Okay, so let's start. Continue our lecture today. So who will be number 3 in your group? Can you share?
It was quite straightforward, a little bit the only issue was that we didn't know that we should like resize the transistors on the step 4 stress verification.
Oh, resizing.
Or other discussion form, there was something, there would be done something because the stress on the M3 transistor, the VDS goes over VDD.
Okay, let's check it during even if we don't have much time, let's try to check it. Yeah. Other comments you have? No? Okay, let's check it. Okay, who is number 5 in your group?
Yeah.
Okay, yeah, can you share yours?
Really interesting, really long. In the stress part, there was the issue that for example, I consider that every peak should be under the stress level, so that all transistors are like I took the maximums of the voltages, so that the maximum should go under the 1.1 volt, and using the same topology, I didn't manage to get it. I have done other things. So others from our group also have to do modifications in the topology, or then to ignore the max. So this wasn't clear. And then in the tuning of the capacitor, something that wasn't clear was what we do with the modulation of the overall signal. What does it mean, the high? The Vx high? Is it the higher that we get? Or should the error be this sort all over the time? So also in the modulated signal?
We are not looking at the max absolute value. We have to look at the difference. That was clearly written in the CAD exercise document, right? Yeah, so difference of the capacitance voltages.
Yeah. Maybe I'm not expressing correct. If someone can explain better.
The maximum value of Vx is not coming with the 500 microseconds at some point, and it will get some delay. So I think it's a little bit hard to tell which line Vx can get a maximum. And we always make some programs that there are some spikes on the M3's VDS, and we are not sure that is satisfied with the criteria.
Okay.
Generally, it's satisfied, but some moments they have some spikes over 1.5 volt.
Okay.
For the now you speak for the stress, but there is nowhere to. I try to be fast. When we look just short time, we can get the error if this is the VDD and this is 0.99. We can get it to be like that. But when we look the long time, there is this envelope and the modulation. So VDD remains the same, and we might get here that it is indeed in the 099, but what we do in the modulated area?
Yeah, then we need to make sure every cases we have to make sure the BGS, bootstrapped BGS must be within the tolerance range. That was how we do it.
So the 099 should be here. Right.
Yeah, that was how we also solved in quiz, right? For input independent BGS.
Okay.
That is the concept of our bootstrapped switch.
Okay.
So we should not take the best case. We should not take the worst case. Satisfaction.
That probably never managed to do.
Okay, so if you have a certain kind of questions, please post the questions to the discussion forum. Then our TAs can try to answer this. Okay, so here on who is number 4? Yeah. Okay.
Overall, I think for the assignment part, there was no little issues. Maybe some inconsistencies with the gradings in the back of the report and in the assignment part.
Okay.
And the main issue, I think, for our group was the time that it took to write the report instead of doing the simulation. So that was the lengthiest part.
I see. That then it's not good situation. Thank you. Yeah, we will think about it. How to reduce the report writing time. That's not.
Adding to this, there was some things that was needed to explain again and again.
Oh yeah. Sorry about this. So that is misalignment with our TA. So we will try to make sure that cannot happen again in next CAD exercise. Okay, so then thank you for sharing your thoughts. So let's run our CAD exercise. So here, let me see, CAD 7. So I will just skip this introduction part, which is generic explanation. So we can start from step 1. So basically, I prepared the sampling switch here, the MOS and capacitor, and I prepared all the steps, Bootstrap 1, 2, 3, and 4, and other setups are just very generic. So you have BSS, VDD, and input here. Let me assign this one as a F-in. And you have standard butters here. And within the Bootstrap, this is how it looks like. Just a minimum sized transistors with exactly same as this setup. Minimum size, and minimum size. Okay, so was this step 1 clear? Straightforward?
At what stage there were different opinions was with the clock. So will you do it like as you do? Is it enough to just give the clock? Do we need to use the non-overlapping clock? And does this have effect to the outcomes of the exercise?
It was not mentioned here. So you if you had such a question, you can run simulation and then compare, right? By adding non-overlapping clock generator if you had such questions. But in this case, we just assume that we just use the inverters. So the easiest way and fastest way is running simulation and after building the test bench. Okay, so we are applying sine wave 490 kilohertz. So here, let's check 490 kilohertz and amplitude 500 millivolt, DC bias 0.5 volt. This way. Okay, then let's run it. And the sample frequency I set 1 megahertz. VDC should be up. VDD 1 volt. And let's run it transient simulation for 2 cycles of input frequency. And let's plot it. Okay, so let's compare baseline MOS switch and this bootstrap switch for step 1. So here we have input voltage, we have clock, and we have output 0 and output 1. And let me drag it down. Of course, you can also plot a clock bar, which is input to bootstrap 1. So clock bar is assigned specifically here because for clock bar is high, then MOS transistor is turned on. That goes to hold phase. So we invert polarity. Let's just plot clock, and we can see that this is input, this is output of baseline switch, this is output of bootstrap switch. You can see that it very well follows well, right, for the high input voltages compared to baseline switch. And let's also have a check VX node, which is, I already set it up here. Input and Vin plus VDD, Vin plus VDD. And here X1 and clock bar and out. Okay, we already have checked out 0, 1, so let's just check this way. So you see that in Vin, this is the input voltage plus VDD, and we have a clock bar, and this is a X node of this, the first bootstrapped switch. You can see that it looks quite weird at this region. So for the X node, it nicely boosts and follows very well input voltage plus VDD, right? But for X1 node, so here X node, we expect that during the clock bar, then it boosts VDD plus Vin. But after that, we expect it go down to ground. But you can see that when input is high, there is some kind of a following effect. And when input is low, then it nicely attached to ground. So why does it happen? So that is because of here, P, which is Vin plus VDD, same as a yellow. And clock, let's plot, so this clock is actually connected to clock bar. So here, clock bar. So this is a clock bar during this phase. So clock bar is indeed gate voltage is smaller than the source voltage, such that this PMOS is turned on during this phase. So even if it looks like ideal, it cannot work correctly in real case. Of course, it looks like it is operating well, but if you plot the current here, current. So for plotting current, you can go output, save all, and just check this current mark. It is by default, it is unchecked. So you can see that there are a significant amount of current is wasted during this range because of this situation, such that in this situation, what is happening is that this PMOS is turned on, this MOS is also turned on, so there is a current just a waste, which is a power waste. We don't want it. And for the PMOS body, this is obviously it should be attached to the highest voltage. If we attach this one to VDD, then this is also same situation. If this one is VDD, then VP is higher than VDD, then this PN transistor turns on, then circuit doesn't work. So let's go for the next step. So step 2 is now we are adding the control switches to switches on to V-in input voltage or switch off to disconnect from V-in. So for this, I also prepared. So here X1 clock bar, output 1 and output 2. And let's compare. X2 also. And let's drag our downside. Input was VDD and X1, X2. Let's put it this way then. So you can see that X2 now settles down quite well during the hold pace when clock bar is high. So this is possible because now we are driving this node voltage not V-in but resetting to ground, such that if this one is ground, then it for the hold pace it becomes to VDD. Then this transistor is fully turned off. That was step 2, and other things are very quite straightforward and similar, right? For V out 1, 2, we have a very similar situation. So let's move on to step 3. Now we are removing. Oh, by the way, so I also used the same circuit dimensions here, all minimum sized. Just by all minimum sized. And Bootstrap switch 3 is also same. Minimum size, minimum size, minimum size, minimum, minimum, minimum. And 4 is also the same. Minimum size, everything is a minimum sized. Here. And it is exactly the same circuit to the figure, diagram here, images. Okay, so step 3, we are now building the Bootstrap capacitor. We are not using either DC voltage shift. So here, let's plot it. So by the way, so we are also attaching the PMOS body to the highest voltage. Otherwise, if we just connect to VDD as we discussed, then if VP goes higher than VDD, then this transistor turns on. So which is not what we want. So verify that CB charges to approximately to VDD. Let's plot this one. So V-in, clock bar, Vx, voltage across CB. I prepared voltage across CB. So you can plot the voltage across CB by connecting differential net here and here. You can plot it. And let's compare X2 and X3 and output 2 and output 3. And let's do it. Then we have input, output, clock bar. And let's also divide separately for the capacitor voltage. Then you can see that CB charges to approximately VDD during the tracking phase. You can see that this is a tracking phase, right? For the tracking phase, this one is quite closer to 1 volt. 1 volt. So now I set as a 100 femtofarad. So as it was suggested and recommended, let's run it for 50 femtofarad. Let me see. Let's disable all the plot. Let's run it. So it was previously 994. If I press Control R, it will refresh. Then you can see that it becomes to 990 because I decreased the amount of bootstrapping capacitor. So this is exactly what we have checked during the quiz. Oh, yeah. That question?
Try to run it 10 times more time.
Sorry?
About all the problems what mentioned there, for example, try to run it for transit for 40 micro, 100 micro.
For transistor size?
For the transit, the time, how long? that's what I mean. That is the
Which one?
Yeah.
This one to
40, 60, 100. I ran it 100.
okay. Let's see.
No, I mean 100. Okay.
I just increased the number of cycles, so you can definitely just check it, right? So how many microsecond?
I ran it 100 micro. I think it's the same what you run now.
Okay. Okay. Then
Okay. How you get it? Yeah. So then we have this modulation. Also in X.
for the output 2 and output 3?
For the output, also for the X node.
X node. Okay.
That's what I mean. That this part, when we get now,
Okay. This modulation, right?
no, get it again more.
This one?
Yeah. Here, for example, at that stage, or at that stage, or at that stage. Here we get the perfect, but here.
Yeah, that's what I mean. So you have to make sure this is also satisfied.
So to make this to be perfect, like on
Yes.
the perfect side.
Yes.
Okay.
That's how it means for a bootstrap sampling switch, right?
Okay.
As we solved in quiz.
Okay.
We have to make sure
but
VGS is doesn't dependent on R int.
different on quiz in theory and different when looking at the simulation.
Oh, that's how we have to design circuit, right?
Yeah.
We have to apply theory to our circuit analysis.
Yeah, just don't know because when in the first round when I ran, because I ran many times, when I ran the first time it was in short view, short time window, everything was perfect. Okay, nice. Then when start thinking, okay, let's see how it goes more, then it starts the mess.
Yeah, then you have to make sure. So that is a quite nice point. That is nice one because we have to verify our circuit in many other cases. Otherwise, if you really spend a lot of time and you design chip and you fabricate chip, and if you see that your circuit doesn't work as you expected, then this is how the situation can happen. So we need to make sure our target specification is really met. Yeah. Okay, so here now we have a VGS. So CB charges to approximately to VDD, right? So here it charges to approximately to VDD, right? Of course, there is some discrepancy between here and here. So it is a 10 millivolt discrepancy, right? So check whether VGS M2. So VGS M2 is a sampling switch here, right? The switch. Gate source voltage. Then you can see that during the tracking phase, you can see that those are all very well boosted to very close to 1 volt. Of course, as we expected, when the tracking phase, this voltage is equal to the voltage across the bootstrapping sampling capacitor, right? So it has definitely some discrepancy to VDD, but it's quite closer to VDD. So for the charge sharing between CB and the parasitic capacitance at node X, this happens because there is a parasitic cap here, gate to source voltage, to source node. So if we assign, let's say, capacitor, for example, 10 femtofarad, let's assume that we increase the size, or maybe you can actually increase the transistor size. So let's say they increase by 10. And let's see what happens. Okay, let's make it quick. Then here currently it is a 10 millivolt difference. So now you can see that it is increased. The difference is increased to 25 millivolt because of parasitic capacitance here. Of course, in this, its bandwidth will be increased because of lower R-on switch, but the amount of bootstrapping will be decreased because of this parasitic capacitance. And compare the output waveforms with the circuit in step 2. So here, let's finalize before we end. So let's plot it here, right? So for comparing output 2 and 3, let me run the simulation again. So now let's take it 50. Refresh. Then you can see that output 2 and 3 are quite nicely aligned. And CBT is also boosted through during the tracking phase, and X2, X3 are boosted quite well. So in the end, this one is nicely matching to what we call what we built using ideal DC voltage source. And observe the voltage at node X. We also did it, and if doesn't go to VDD, then try increasing CB. So for example, if we assign only 10 femtofarad, let's see what happens. Then you can see that it is quite reduced to 950 millivolts. Still, it is quite successful and let's say good, but there is such effect. Okay, so due to time limit, before I conclude, there is a step 4, right? Let me point out one important matter. So why do we need to take care of transistor stress? That is because here, X node reaches as high as 2 volt, but this transistor, VDS rating, I mean the maximum range must be within 1 volt. The worst case 10% higher as a 1.1 volt is the maximum, but it should be around 1 volt, the maximum. Otherwise, if you check the current, you can see that its current is quite large in this region. There is a continuous current because of this high voltage. And in reality, this is actually much bigger than what we expect, because it is already higher than what we can assign for the transistor. And also you can check from this transient simulation environment. Oh, this is not shown, not yet. But anyway, so this one, VDS, is actually click up. Okay, so this VDS is actually higher than 1 volt, which is not good. And also VGS or VSG of this PMOS transistor, let me see, here and here. Then you can see that this PMOS transistor swing is also as high as closer to 2 volt, which is not good. So that is the reason why we need some protection circuits here. We need to cascode MOS, and we need to protect our PMOS transistor by doing so. So we can continue this CAD exercise demo next week. So thank you. So we will have a short break and we will have a quiz.